Hi everyone, welcome to fine tuning of DistilBERT for multi-label classification. We will start this video with the help of explanation what is binary classification, multi-class and multi-label classification. Thereafter I'll take you through the database and then some description of Hugging Face site and the IMDb site. Thereafter we will be doing some text analysis. After this analysis we will be moving toward the label encoder, and thereafter we will start doing the model building. In the model building I'll be showing you how you can build your custom data set. Along with that, how you can build your custom evaluation metrics for multi-label classification. Thereafter I'll be showing you how you can do the training, and then finally you can evaluate your model. Once all these things are done, then I'll be showing you how you can download your model so that you can use it for the later purpose. Then we will be doing the real-time prediction or real prediction based on a movie description, and then we will be doing the prediction, and then I'll be showing you how you can get these string values instead of these number values. Alright, so without the wasting time, let's go ahead and get started with this coding. I'll be showing you step by step detailed coding for this lesson. For a multi-label classification, let's assume that you are given their multiple classes. In that case, there is probability that in one class, in one round of the classification, a multiple class can be selected. You can understand that with this example. The first time, if you are using binary classification, then your model would be able to predict either dog or not a dog. That means there would be one class, and then on that one class it would be able to tell that either 1 or 0. That means your data belongs to that particular class or not. In case of the multi-class classification, there are more than 2 classes. In that case, your model would be able to tell that in what is the particular class for a given image. In this image, you will see that there is a plant, there is a dog. Alright, but in this case, you see there is more focus for the dog. So it is saying that the probability for the dog is 0.5 and for plant it is 0.4, although there is some probability. Now, one thing you see there is a high probability for the dog and the plant. So this multi-label classification solves this problem. When there are more than one classes in the image or in any data, be it text data, audio data, whatever the data, when there are more than one classes in the data, then you can use the multi-label classification. With this image, it is very much clear that there is a dog and there is also plant here. So in this case, if you feed this data to your model will output 2 classes, dog and plant. In multi-class, your model will output 1 class, that is the dog only. But in binary classification, it will tell you either 1 or 0. That means it will either say that it is dog or not a dog. So for our example purpose for this multi-label classification, we will be using the IMDb movie data set. You can click on this link. It will lead you to my GitHub repository, Lakshmi Merit all CSV ML data file. And in that, I have IMDb movie data. In this IMDb movie data, we have multiple columns, like we have title, genre, and description. So what we are going to use here, we will be using here genre and description. So we will use this description, a movie description, to predict the genre of the movie. There are many more columns for this data, but we are going to skip those or discard those other columns. There are these two only columns which we are going to use for our purpose. There we have genre and the description. Just to know more about this genre and description for a movie, you can come to this IMDb movie, and then in this IMDb site, if you open any of the movie, let's say you open here Napoleon. So you open this Napoleon, as you open it, you will see here the 2 things. One is you will see here genre, and then you will also see here the description of the movie. So you have action adventure, and the biography. This one is the genre of the movie, and there is the description. So we are going to use this description to predict these genre. And one more thing you should notice here, that in our case our data have only 1000 lines. There it is 1001, that is first line is for its header. So there are just 1000 lines of the data. So data is very much limited. It's not like a huge data which we can utilize with the transformers. But anyway, this is a small set of the data. It would be a very good fundamental background for you to use multi-label classification with transformers and DistilBERT. So this code you can use for your own data, or you can expand this IMDb movie data for 50,000 or 1 million rows to get a better accuracy. To download this data, you need to click on here raw. Once you click on raw, it will open here this raw file. Then this raw file you need to copy it from here, and then you need to read that here. But before that, let me connect my machine with the GPU here. Thereafter, you need to click on save here. Once you have connected your machine with the GPU, then you need to uncomment here pip install accelerator and the transformer, and then you just need to run this so that you can have latest version of accelerator and transformers. As you know that we have been using a lot these Hugging Face transformers. Let me just close this and open this one. So in this Hugging Face transformers, we will be using here a DistilBERT model. In meantime, let me open your DistilBERT model for you. Here, while it is installing, in meantime, I can explain you this DistilBERT base model. So we will be using DistilBERT base uncaged model. Alright, this model you can use. So the default model, the model which we see here, this is used for fill the mask or the masked language modeling. But we will be putting the header at the top of this model to make sure that it works for the classification. All these stuffs we will be doing here. Alright, so this library installation is done there. Let me just close this one, and then I can get started with writing the code here. So the first of all, we have to read our data. For that we import here pandas. So I write here import pandas as PD. Thereafter I write here df is equal to the pd.read_csv, and then I give here the data path. Then you can check it with the df.head. Now I'll be seeing here a multiple columns. As I told you earlier, we will be using here only genre and description. Rest other columns we do not need. For that, we are going to select here genre and the description. That either we can select it from here, or we can write it here, that use column. I write here use calls. Which calls we are going to use? We are going to use here description and genre. In fact, I'm going to put here the description first so that I can see the description first, and thereafter the genre will come. Let's go ahead and run this. Now here I see, although seems like the genre is still coming at the first, but it's not a problem anyway. So we have here a genre, and then there is the description. Now, as you see that for each description there is multiple genres. So this type of the problem belongs to the multi-label classification. Let's go ahead and do some basic steps to clean this data. And before that, we need to check the shape of the data and some duplicates. If there is a duplicates, all these steps are just the sanity on the data. So you can check that df.shape, which should be 1000 cross 2. That is perfectly fine. Then df.info will tell us about the information about the data frame, where it says that there is total 1000 entries and 1000 not null values. That means there is no null value. We just need to check that if there is any duplicate, so which we can check it with df.duplicated.sum, and then we just run it. we see here there is a 0 duplicated value. That's mean there is no duplicate movie entry here. Once all these steps are done, now the two things we need to do more here just to understand about our data, like how many characters are there in the description. It will help us to identify that how many tokens we need to explain our description in the transformers. And in case of the genre, this genre will help us to understand that if it is having imbalanced data, which is very much likely. Since we are using only 1000 rows, then there is probability that this could be a little imbalanced data, but not a problem. We can go ahead with this. Since this is just a demo tutorial, if you are using your own data, then you can have the large data set just to avoid any case of the imbalancing in your data. So I'm going to use here just for a description analysis. So I write here description str.len.plot.histogram, and in this histogram I'm going to use number of bins here 50. I just run this. What I see here that a histogram for the description is plotted, and this length, what we see here, that this length is the character length, and seems like more than we do not have anything more than 500 character. Do remember this is character, not the token. In general, on average 4 to 5 characters belongs to the single token in English language. So basically we can assume that any of these tweets which we any of these movie description which we have must have less than 100 tokens. That's mean if we are going to use the DistilBERT, which have maximum context size 512 tokens, so we can simply use this DistilBERT without any lose of the context in case of the description data. So we are very much safe to use our DistilBERT data. Let's go ahead and see about the genre. So for the genre, we cannot use directly this function to plot the genre, because the genre have here the the comma values there, and this one is the target value. So we have to first combine everything together, and then we have to see that these individual genres there. So for that purpose, what we can do here, I can write here df genre is equal to df, and then we have here genre.str.split. First of all, we are going to split it with the comma so that I can make it as a list. This genre is now here as a list. Now this genre, we need to identify that how many how many values are there. So if you see it here that the genre, you will see there this one is as list, and if you check here with the value counts, probably you would not get the result. Okay, yeah, so the actual result which we want, that we will not get here, because all these multiple genres are combined here. We do not want this like we do not want it like this. We want it like individual genre values. So for that purpose, what we will do here, we are going to use here list comprehension method. The use of list comprehension method is very simple. You can just simply write here for gen in df.genre. Thereafter, you know that this gen is this particular row or any other row. That means it is taking a row by row. Now we need to iterate over this as well. So I write here for g in gen. Now we are iterating over these individual values. Then I put g here. Now if you check it, you will see that this one is genre count. So I write here genre counts equal to like this. Thereafter, you would be able to see this here. Alright, so this has combined all those, the multiple values as the individual, I mean to say that those individual list as a combined list. Thereafter, we need to get here the count. So there are many ways to get the count. I'm going to use here the pd.series method. So I write here the pd.series, and then pd.series. In this, I put here this genre count, and then I put here value counts. So with this I'll be getting here the counts. So it says that we have maximum 513 for the drama, 303 for action, comedy, adventure, thriller. So many genre is there. But if you see it from here, the last you will see the less numbers for the musical, western, war, music, sport, and the history. Probably we can assume that whatever is there above 100, we can assume that these will produce a good result. But here we have a less number of the genre. These might produce low quality result, or result would be biased toward these values which are more here. But again, I should tell you that this is just a test data which have just 1000 rows. In actual world, when you are using this model for your industry, it might have millions of rows or 100,000 rows, in which there is less probability that you would be having something like this. Alright, let's move ahead. Now we know that our data is a little imbalanced, but we are still moving ahead. Now the time to do the label encoder so that we can get started with multi-label classification. So here I write here, label encoder. I'm just going to write here the label encoder. So for label encoder, I need to import it from the sklearn. So I write here from sklearn dot preprocessing import multi-label binarizer. Once I import this multi-label binarizer, I need to make an object of this multi-label binarizer. So for that object, I say here multi-label is equal to multi-label binarizer, the same thing which we had used here. Once we get the object, now we know that in our data frame df, which we see here in the genre column, we have our genre, which is here list. Always remember that this multi-label will work only when your data have list values here. So now I get here the multi-label. I write here multi-label dot fit underscore transform, and then I put here the df dot genre. Thereafter I write here as type, and then I write here float 32. So what it is going to do here, it is first going to convert this genre into the one hot encoding, or you can say as a dummy variable, and then those values are going to get converted as the float, because this multi-label classification model works only when your multi-label is shown as a float value. Thereafter I write here the texts. Okay, so this should be stored as labels. Currently it is not getting stored in any variables. I write here labels equal to the multi-label dot fit transform. Thereafter I write here the texts is equal to the df dot description, and thereafter I write here to list. So now we have our labels and the text data. We can simply print our labels just to understand that how this label is encoded here. As you see there, this one is now float 32. This float 32 or this label will be used for the classification. Let's go ahead and see our text data similarly like we see here our label data. And for the text data, you will be seeing our text data as shown here. We are not doing any kind of the pre-processing on the text data, since we are going to use this as it is without any pre-processing, although you can try out some pre-processing and you can then see if you are getting better accuracy. So I'm just gonna print here the first 5 the rows there, and these are just for reference in case of the future reference. Alright, now we have reached at the stage where we can do the model building. So this model building is a very much simple process, but before that there are few things which you have to do here. First, you have to import all the necessary transformers libraries. Thereafter, you have to make your custom data based on this text and the label values. Then you have to do the tokenization. Thereafter, you have to build their multi-label metrics, because multi-label classification metrics does not work like the multi-class classification. In this multi-label classification, there are multiple classes which you need to check there if there is any overlap in the classes for its accuracy prediction. So a standard accuracy will not work with the multi-label classification. Other than that, as you move forward, then we will build there a compute matrix. Thereafter, we will build their training arguments and then trainer, and thereafter we will do the training. Alright. Let's go ahead and import the necessary packages. So I write here import torch. Thereafter, I write here from transformers import DistilBERT tokenizer. Alright. Now here there is two options. Either you import DistilBERT tokenizer or you can import auto tokenizer automatically. So this auto tokenizer would be also able to do the same thing what this DistilBERT tokenizer is doing here. Similarly, you can import here again in the next line. I'm gonna import from transformers import DistilBERT for sequence classification. There are multiple type of the problem statements here. So if I import this DistilBERT for sequence classification, now you need to come here just to understand this. The default model which we have here, DistilBERT based uncaged model, this works only for masked language modeling. But if we import DistilBERT for sequence classification, this will automatically add their classification head on the top of this masked language modeling. So it will make sure that this model should be used for the classification. This is one way to do, and similarly we can use here auto model for sequence classification. So that we can also use here auto model for sequence classification. We should be having somewhere, otherwise you can just write it here. Now you can see it here. Alright, so this part and this part both are the same thing here. This also says that whatever the model you give there, these two will automatically put their classification head at the top of the model. There is some limitation with these type of import. Like for this, you can only give there a BERT based model. For these type of model, you can give there any kind of model for the classification. Alright, that's the difference between these two. Thereafter, I'm gonna use here sklearn model selection to import train test split. Thereafter, I write here from torch.utils.data import dataset. That's all we have here. Okay, so here we have auto tokenizer, DistilBERT for sequence classification, auto model for sequence classification. Then we have train test split, and then we have here data set. Alright, now let's go ahead and move ahead here. We are going to do here train test split for our data which we have inside the text and the labels variable. For that, I write here train texts. Thereafter, I write here validation texts. Thereafter, I write here train underscore labels, and then I write here validation underscore labels here. Alright, so we have here train text data and validation text data. Similarly, we have train labels and validation label. Thereafter, I write here train test split which we had imported, and in this we are going to pass our X data, that is the input feature, which is texts, and thereafter output the target label, which is the labels. Thereafter inside this, I'm gonna say that the test size I'm gonna use here 0.2, and apart from that you can use any random state, otherwise you can leave that as it is. So I'm just gonna use a default random state, which is 42. Alright, let's go ahead and run this. So we have got here the train text data, validation text, train label, and test labels, validation label. Thereafter we are going to assign the checkpoint. So the checkpoint is here, so I just copy it from here and then I write it here. Checkpoint. So the checkpoint address is DistilBERT base uncased. Now I need to load here the tokenizer. So for the tokenizer, I'm gonna use the DistilBERT tokenizer, although you are free to use the auto tokenizer as well. So I write here the DistilBERT tokenizer, which I had already imported here, dot from pre-trained, and then I give here the checkpoint. Alright, so there is the checkpoint. Thereafter, I'm gonna use here our model. I mean to say that I'm gonna load our model here again using DistilBERT. So I'm gonna just copy this DistilBERT for sequence classification. I put it here, and thereafter I'm gonna say here from pre-trained, and then I write here checkpoint. Thereafter I need to also tell that how many heads it need to attach in the output for the classes. So for that purpose I have to tell it how many number of classes are there. So how many unique classes are there? You check their labels are there. If you get the length of the labels, you will get the total number of rows, but if you get the length of the first row, you will get the total number of class. So I put it here as length of label 0, so it will tell us that there is 20 classes. So there will be a 20 output neural cell with the softmax activation function will be placed at the output, which will be used for the prediction. Alright, thereafter we also need to tell our model that this type of problem, this particular problem is multi-label classification. So I write here the problem underscore type is equal to multi-label classification. Alright, once all these things are done, then you just simply need to run this. So it is going to download the tokenizer. In fact, it is going to download DistilBERT base uncased, and then the same thing will be used for the tokenizer, and the same thing will be used for the model building. It has successfully downloaded. Once your model is downloaded, if you remember previously I told you that after model download, we have to build here the custom dataset. Alright, so for the custom dataset, you need to understand this a little bit. Let me just add here a page, and then I will explain you that how you can do that. So for this page, let me just explain that the custom dataset, how it is going to work in our case. So I'm just gonna add here a pin for our purpose so that I can explain you. Okay, so for this custom data which we have here, okay, I'm sure it should be visible to you, otherwise just let me increase the thickness of this. Okay, so there we have a custom data set. In this custom data set, there are three parts of this custom data set. One is initialization, another part of this data set is length, and the third part of this data set is get item. So these three methods we are going to implement into class and the class name you can give any class name which you want to use for your dataset. For my dataset, I'm gonna give the name as custom dataset, so that I can initialize this, and then inside the custom dataset you need to extend this with the dataset. So basically you are passing this, you are telling this custom dataset as this one is inheriting this dataset class here. So this dataset will be treated, custom dataset will be treated as a standard dataset. And then this dataset is coming from the torch. As you had seen previously, we had imported it from the torch. And then we will be using there the validation dataset and our train dataset. Alright, so this train and validation dataset will be used for the custom dataset to build a proper training and validation dataset. And then the input will be also passed there inside this init. You can put here the double underscore and here as double underscore, double underscore, double underscore, and here as well you have to build double underscore. This is what we are going to build now with the code. Do remember these three methods here. Alright, let's go ahead and build the custom dataset. So for custom dataset, I'm going to say here class custom dataset. In this I extend it as the dataset. The first method I write here init method, and then in this init method it takes the self context. Thereafter I pass here the text as an input and then the labels as the input, and then I also pass here the tokenizer, and then I pass here the maximum context length for the model, which I set as the 128. This is the first definition. The second definition, as you remember, that is the len, and in this I do not pass any parameter. Then this one was the first one. Thereafter we have here the second one. Then let's go ahead and build the third one. So the third one was the def double underscore get item double underscore, and then you put here the self and then the idx. So this idx is index while iterating the dataset. Now we need to implement here the init method. So init method is very much simple. You just need to write here the self dot texts is equal to the texts. Thereafter you need to write here the self dot labels is equal to labels. Self dot tokenizer is equal to tokenizer. Thereafter you implement here self dot maxlen is equal to maxlen. What's the purpose of using this? This will make sure that you do not need to pass these parameters in other methods. So the other methods you can directly in other methods you can directly access these parameters. So here I return the length of self.text, which is passed from here itself. Thereafter in get item method you can implement rest of the things where main part of the tokenization will happen. So I get here the text. Now as you see here, this get item is this one is being done iteratively, all right, after one index to the another. So you know that your text's data is a list there, list of the data. So if you put their index, then you will be getting their individual text data. And this str will make sure that any kind of the data will get converted as the string data. And then I put here self.texts. Thereafter inside that I put the ID number from which I want to export the text data. Thereafter I put here the label is equal to the torch dot tensor, and then I put here the self dot labels, and then I put here the idx. All right. So I have here the get item and then self idx text is equal to the str, self dot text idx is here, label equal to the torch dot tensor, self dot labels idx. Thereafter I have here encoding is equal to self dot tokenizer, and then text truncation is equal to the true. So what is happening here? First I converted this as the single, the text data I got here from the IDX, and the respective label I got here inside this label. Now I need to do the tokenization. So I do here self.tokenizer. Then I pass their text data. I make sure that if anything is greater than the maximum length, that is the 128 tokens, then that will get truncated. And if maximum length of the text data is less than 128, then the padding will be used there. So I write here the padding, and the padding, it will be used till the maximum length. So it writes something like this. Thereafter the max length I define here, the max length is equal to the self dot max length, which I had defined earlier. After doing all these, then I write here return parameter. So this return tensor is equal to the pt. That's mean it will make sure that a PyTorch tensor is returned with this encoding. After this tokenization, then I'll be returning these as the dictionary, in which I say here input underscore IDs. These are the standard keys which a model will expect. I write here encoding, and then inside encoding, as you might have seen my previous videos, it has there multiple keys. The first key is there like input IDs, and then I flatten that input IDs. Other than that, it will be also having their attention mask. So I put here attention mask. Thereafter I put here the encoding attention mask. Then I put here the flatten. So you see this encoding have here input IDs, flatten, attention mask as the flatten. So finally we are going to attach our labels as well. Do remember, all these are default keys a model will expect. You cannot change the name of these IDs, otherwise it will throw the error here. Now I got here the label as well. So we got here label and input IDs and the mask, attention mask. That's all you need to you need while building this custom data set. I just need to run this. You just run this, it will successfully run here. Now I can get the trained data set. So I write here trained data set is equal to custom data set. Inside this I write here trained texts data, and then I write here the train labels. Thereafter I write here the tokenizer. Then I write here the validation data set is equal to custom data set, validation text data, and then similarly validation labels data. Thereafter you have here tokenizer. Alright, so we have here the train data set, the custom data set, train text data, train labels, tokenizer, validation text data, validation label, and then we have here tokenizer. Alright, let me just run this. Now you will see here your data set is ready. So you have here the train data set, and then you have here the validation data set. Alright, so these two data set is ready here. You can actually visualize, or you can see these data. This is the first validation data set. These are input context, and the rest are the padding which you see. This you can verify with the attention mask here as well. and it has here seems like the 3 classes, this one, and this one. That is why these are known as multi-label classification. Alright, let's go ahead and move ahead from here, and in the description let me again tell you that the few more things are left here. So after completing this custom dataset part, which is done, now we need to build here evaluation metrics. So this part is also going to take a while. Evaluation metrics. Why this part is needed? See, the standard multi-class classification accuracy method will not work here. We have to make here multi-label the evaluation metrics. So for multi-label evaluation metrics, you see the difference here. In case of the multi-class, if your class is 1, your output is 1, then you say that it is okay. And if your input is 1, I mean the true value is 1 and predicted value is 0, then you say that this one is wrong. This is the case of multi-class. Alright. Multi-class, or you see that the binary prediction. But what happened in case of the multi-label classification? There are multiple values, 1, 0, 1, let's say. Then you get some predicted values here, in which you get 1, 0, 0, something like this. Although you see there, these all values are not correct, but still their one value is correct. So you cannot say that it is either wrong or true. There is some overlap. That is why this multi-label classification which we have here, alright, this one is a little bit tricky to implement. So its accuracy will be different what we get in our regular multi-class classification. So for that purpose, we have to implement here the multi-label metrics. So for that multi-label metrics, there is some process to implement, like we can implement Hamming loss, we can implement their ROC AUC curve or ROC AUC score. So these are the two important points in the multi-label classification. So those part we are going to implement here. So I write here multi-label classification evaluation metrics. So it's like this here. Now what I get here, import numpy as np from sklearn.metrics, import ROC AUC score, thereafter F1 score, thereafter you have here Hamming loss. Transformers, import eval prediction, then you import here torch. Alright, so I write here the import numpy as np from sklearn.metrics, import ROC AUC score, F1 score, and then you have here Hamming loss. The transformers you have here imported eval prediction, so this one will be used to evaluate our prediction, and then obviously the torch as usual. Alright. Okay, let's complete our multi-label metrics here. So I write here a method def multi_labels_metrics. So in this, I pass here first the predicted value, which is passed as the predictions, and then I passed here the true value, which is passed as labels. Thereafter, I pass here threshold value, which is th, or you can just simply write its name, which is threshold is equal to 0.3 or 0.5, whatever you want. Why this threshold value is different? For this, you have to come here and then check it. You see, in case of binary classification, If this predicted value is greater than 0.5, then you say it is yes, otherwise no. In case of the multi-class classification, you similarly, the same thing you do, but one thing you see there, the sum of these probabilities are equal to 1 always. For this one, the sum of these values are equal to 1 always. But the sum of these values are not equal to 1. You see there, the sum of these values are greater than 1. So in this case, the general practice is to make it 0.5. Although if you want, you can make it a little less. It depends on how much precision and recall you want. In some cases, I have tested that if I put their values less than values less than 0.5, then we get the better value. So that's why I am choosing here 0.3. But the standard practice is 0.5. It depends, right? The type of the data which you are using. Thereafter, I'm going to apply here a sigmoid function on the prediction. So, this prediction comes there. As the, the standard logits there. So on those logits, that means the raw values, you have to apply their, the activation function. So I apply their sigmoid activation function for each of those, the output neural cells there. So I apply their sigmoid. So I write here, first of all, sigmoid is equal to the torch dot neural network. Then I write here the sigmoid. Thereafter, I get here the probabilities, which is the probs. Then I call here the sigmoid, and inside this, I call here the torch dot, the tensor. Inside this tensor, I pass these predictions. So what happened here? Whatever the predictions I'm getting, first of all, this sigmoid activation function is applied just before the output. So how this is working? Let me just explain that again. Let's say you have many classes as the output, which we know that there is 20 classes, I think. So whatever the classes are there, these are the neural network cells are there. All right. Then on these cells, we are applying here sigmoid. And whatever the output we get here at these stage, what we see there, these are known as logits here. Alright, so on these logits, these sigmoids are applied here. Then finally you get here the final probability. So this one is the final probability. So final probability, you can say that there is, you have sigmoid and then you put there this logit. Alright, so that's how this works here. Let me just go back there once again. So you got here the probability. Then you need to get the y predicted value. So these probabilities can vary from 0 to 1 in between these. Now what I do here, that you will be getting here the array. So this one is, you see there the array, and for each of these you might get the probability of 0.9 or 0.1, then 0.3 dot dot. So what I do here, I will compare each of these values with the threshold value which I had already set there, 0.3. So if any of these values are greater than threshold th, then you will say that it is true. That means it is 1. So whatever the class have values, these probability values greater than this threshold value, then you will see that it is true for that class. So we write it here, ypred. First of all, I put everything as np.grows, and the shape of this would be the probabilities which we have there, the shape of probabilities. Thereafter, I write here y underscore pred equal to, in fact, since this one is the numpy array, now I need to get all those index where these probabilities are greater than threshold. So inside this, I use a technique of np.where, where I'll be changing the values selectively. So I write here np.where probabilities, which is the probs greater than or equal to threshold value. In that case, I put here 1 otherwise it will be 0. Thereafter I put here this y true is equal to labels. So I got here y pred and the y true values. So these y true value, which we already know that these are a set of 1 and 0, and with the help of this line y pred value will be also set of 1s and 0s. Now we have got our the y pred and the y true value as the standard value which we see in our general classification. And now we are going to compare ROC, AUC, Hamming and F1 score. So I compare here F1 is equal to F1 underscore score, F1 score. Thereafter I write here y true value. Thereafter I write here y pred value. And then the average method which I'm gonna use here, that is the micro, or you can just ignore that, it will automatically take the default one. Alright. Thereafter you write here ROC underscore AUC is equal to ROC and AUC, region of curve, alright. So the region of conversion you get there ROC AUC score, and in this you pass again the same values which I had passed earlier, y true and then y predicted value. Thereafter I'm gonna get here the Hamming loss. So lesser the Hamming loss, that's mean the better the accuracy. So I write here the Hamming underscore loss. So in case of these multi-label classification, we generally use the Hamming loss to understand that how much loss it is occurring there. So you put there y underscore true and then y underscore pred here. You have got here the Hamming loss as well. So by typing all these, then we are going to return here the matrix. So I return, I first write here, my matrix. So the matrix is going to be here a dictionary. So the first value we have here ROC AUC, which we already have inside the ROC AUC value. The second one I'm gonna keep here Hamming loss, which I have in variable known as Hamming. The third one I'm gonna keep here F1, which I have into a variable of F1. Once all these things are done, then I just return this matrix. Now you see there, this is a little, moreover you see it is the same thing what we have been doing. Only the difference is that we have made here a different, a separate function, actually a separate method. Once this one is done, now the final, the compute matrix method we are going to implement, which is very small, just a few lines of code. So I write here def compute underscore matrix. So what I write here, the P, that's the eval prediction. So during the evaluation, these method will be called here, and this is kind of, you can say that the extension of the eval prediction, which is the prediction during the evaluation. Then in this I write here the preds is equal to P dot predictions 0. Actually it is going to check that if prediction is tuple, it is going to take this 0 value, otherwise it will take the P dot prediction as it is. So it check that if is instance this P dot prediction is tuple, then it is going to execute this one, else you write here the P dot predictions. Alright, so in this case now we have got this pred. This pred now we can pass to the the multi-label matrix. So that's what we are going to do here. I write here result is equal to multi underscore labels underscore matrix. I pass here predictions is equal to preds. Then I pass here labels is equal to P dot label underscore IDs. Then you return here result. Alright, so you have here multi-labels metrics, then you have here compute metrics, p eval prediction, then you have pred is equal to the p dot predictions 0 if is instance, p dot predictions tuple is p dot predictions. Result is equal to the multi labels matrix, predictions is equal to the pred, label is equal to the p dot the label IDH. Then you return this result. Alright, now we have reached at the stage where we just need to implement training arguments and the trainer. Thereafter we will be ready to train our model. So I'm just gonna build here the training arguments. For this I write here the training. In fact, I'm just gonna write here args. That's the training arguments. So this training arguments and trainer function or the method from the Hugging Face is high level wrapper for the training model. So we can pass here necessary parameters needed for our model. So first parameter I'm going to pass here per device train batch size, which is 8. That means it is going to train our model in the batch of 8. The same thing again here I write per device eval batch size is equal to 8. Thereafter I write here output underscore dir is equal to dot / results. Thereafter I write here number of train underscore epochs is equal to 3. There we have. So the per device train batch size equal to the 8, per device eval batch size equal to 8, output dir is equal to results. That means the model is going to store here inside this result directory. The number of training epoch we are going to use here 3. Once all these things are done, then I write here save underscore steps is equal to 1000. Then I write here save underscore total underscore here limit, which is equal to 2. Alright, so it is going to save this model, or you can say the checkpoint, at every 1000 steps, and it will save it these checkpoints only 2 times here. And then I write here the logging dir and all these stuff. So I'm just gonna skip those parts. In fact, these 2 is also not needed, but you can keep those. I'm just gonna train it for 5 epochs from here. Seems like this training argument is not defined. That means we have to import these training arguments as well. So you write there from transformers import training arguments, and we also need to import the trainer from this. Now your argument is ready. Let's go ahead and prepare your trainer. Just let me check that it is okay. So now you have here the trainer. So the trainer is equal to a trainer. Now this trainer should start as the capital letter. In this trainer we need to pass our model which we had imported at the start of our video. That's the model equal to the model, and the arguments is equal to the arguments which we had just prepared. Thereafter train data set, which we had got with our custom data set. So I write here train data set. Thereafter we have here eval data set, which we had prepared as validation data set. After doing all these, I just need to make sure that compute metrics which we had just prepared should be used. So you need to put here the name of the method which will be used for computation. I just need to now run this, so it will prepare here trainer arguments here. Alright, seems like compute metrics. This one is not defined. Let me just copy it again and then I'm just gonna run it. And okay, this name was there problematic. That name was a little problematic. Alright, so we have got our training arguments and the trainer. Once all these things you have built here, you are ready to train your model. So I just write here trainer dot train, and then it is just going to train your model. It is going to take a while to train your model. We can wait for some time. Alright, now you can see that the training is done here. Let's go ahead and do the model evaluation. For that, I just do here trainer dot evaluate. You just run this. Now your model evaluation will be done here quickly. Seems like something is wrong. Okay, seems like that average one which we had skipped while preparing our multi-level metrics, that is creating a problem here. So what we need to do here for F1 score, I have to give here average is equal to macro, and then similarly for this one I have to give it here as macro. Then let's go ahead and run this, and then I'm just gonna train my model once again here. It may take a while again, and then finally I'll do the evaluation. Alright, so the model evaluation is done, which we see here that it is giving us that Hamming score less than 0.1, and evaluation ROC AUC is quite good, which is around 67-70, you can say that. By just seeing that we had 1000 rows only, and we are using here very heavy model, we can say that this one is very good accuracy. So we do not have here a standard accuracy, and you cannot go with the F1 score. So this one is a proper way to know that how good your model is doing. So this, I believe that is quite good model. Let's go ahead and save this model so that you can use it for a later purpose. I just need to write here trainer dot save underscore model. I need to give here the model name. For model name, I give here the DistilBERT fine-tuned IMDb dataset, and then I give here the name of this as multi-label. Alright, that's what you have model name. Now after storing this model, you should be able to see that here you have DistilBERT fine-tuned IMDb multi-label, IMDb multi-label. So your model is stored here. Now you can use your model for later purpose if you want. And do not forget about to save the multi-label binarizer, because that will help you to decode your predicted output. So for that you can do import pickle, thereafter with open multi-label binarizer.pkl, and the mode in which I'm gonna open this as the write binary mode. Thereafter I write here the pickle.dump, and then I use here the multi-label f. Alright, I just run this. You should be able to see your multi-label binarizer here. So these two are stored here, then you can download it from here. So this will get downloaded easily. The problem you will face to download this one, there is no option to download. So for that you have to convert this folder as this folder as the zip file. So to convert that as the zip file, you need to run here zip -r, that is the run it recursively. Then you need to give the file name which you want to use there. So I write here, let's say just DistilBERT .zip. Thereafter the folder name you need to give there, so I just copy the path here and then I put it here. Let's go ahead and run this. You should be able to see that DistilBERT.zip here after some time. Once this code is done, then you would be able to download your model. Then you can load that for later purpose. Alright, so while this is being done, now we have reached to the state where we can do the predictions on the data. Let's go ahead and refresh this. I get here the DistilBERT.zip. I get here option to download this. So once these two things, I have DistilBERT.zip and my multi-level binarizer, I can use this model anywhere I want. You just need to download your tokenizer as a standard tokenizer, and then you load your model weights, which we have just downloaded. Then you can use your model wherever you want. Now let's go ahead and do the prediction on some data on IMDb data. Let's say the latest we have a movie which was actually, the Marvel movie. Probably here I have a Marvel movie, the Marvels. Well, there I'm just gonna copy this one and then I'll see that it's predictions. So I write here the text data there, and this text data need to be encoded. Let me just explain you the prediction process just for your better understanding. So you have your text data here, then this text data get converted using the tokenizer. Thereafter this one we feed to the model, then this model gives us the output. So that's how it works. So that's what we are going to do here. So we have got text data. Now we are going to get the encoding using the tokenizer. So I call here encoding equal to the tokenizer, and then I pass the text data, and then I say here return underscore tensors is equal to PT. That's the PyTorch tensor. Thereafter I write here the encoding dot to. So we are going to use the same device which our model was using. So the trainer dot model dot device. So this will make sure that we put our encoding and the model either in CPU or GPU, whatever our model is using. Thereafter I write here the outputs is equal to trainer dot model, and then we put our encoding here. Thereafter this will give us the output here. So this output is as a standard logits, which I had explained you earlier that this one is giving us a standard logits like we are seeing here. Now we need to apply here activation function to get converted it as a standard probability. So for that I need to get first of all the sigmoid. So the sigmoid is equal to the torch dot neural network, then dot sigmoid. Thereafter I'm gonna get here the probabilities is equal to sigmoid, and then I need to pass here these logits which we are getting into the output. So the outputs dot, you see you have here logits, and then it is the multi-dimensional array. So in that I need to give here the first array. So the logits 0, or you can say there the output logits, I can squeeze this as well. So I can write it either a squeeze, or I'm just gonna keep it as it is like I have here. Thereafter I write here the predictions. Preds is equal to np dot zeros, like I had implemented it earlier in our compute metrics. In that I had done the similar things here. So np dot wherever the probabilities are greater than or equal to the threshold which we had set there 0.3, I'm just gonna make it as 1. Thereafter our preds are ready here. Let's go ahead and run this. Now you should be able to see that output. Okay, so seems like it is not doing good there, device tensor. Okay, I need to convert it into a CPU. So after the prediction, this particular part, now we need to bring it to CPU. So I put here dot CPU. So it will now bring it into the CPU where we can apply. So we have got here our prediction, but these are the numbers. We don't know the classes. So to know the classes, we can call here the multi-label binarizer. As you know that in our multi-label dot classes, we have all the classes which are used during the conversion. So these are the classes. Now I need to use this multi-label binarizer to convert our prediction as the classes. So I write here the multi-label dot inverse underscore transform, and in that I call here preds dot reshape 1, -1. Alright, so this reshaping is necessary to make sure that your this spread gets converted into a multi-dimensional array. Currently it is just the one-dimensional. This will make sure that it gets converted as two-dimensional. Let's run this. You will see here. Alright, so once all these things are done, just run this. Now you will see that this one is action, adventure, and there is comedy. Although this is not perfectly a comedy, but if you watch this movie, you will see a little bit comedy inside this movie. You can get any other movie and you can do the prediction as well. So basically now you know that how you can train your DistilBERT model for multi-label classification. Now you know that how you can download your model. Alright, so this is all about in this lesson. Thanks a lot for watching this. Please subscribe this channel and like this video. Alright, I'll see you next lesson.